Good afternoon and welcome to the Doble Engineering Monthly Webinar Series. My name is Monty Ashigi. I'm the Director of Client Service Accounts and your host for today's webinar. I'd like to thank all of you for taking time out of your day to join us. Our webinar today is entitled Testing Three-Winding Transformers and will be presented by Norbert Gilbert at Doble Engineering. Before I introduce Norbert and turn over the presentation to him, I wanted to go over a few procedures to ensure that today's webinar flows smoothly. First, all attendees' phones and microphones have been muted in order to eliminate any background noise which could interfere with the presentation. We do encourage you to ask questions, and we ask that you submit your questions using the question feature on your screen. We'll collect all questions and present these during a brief question and answer period after Norbert has completed his presentation. We'll read and answer each question verbally, one at a time. If you'd like to get credit for continuing education units or earn one professional development hour, please answer the question related to our webinar today in the feedback form, which will be sent to you at the end of the webinar. A certificate for credit will be sent to those who complete the question. Finally, I'd like to mention that our session today will be recorded and the link sent to all registered attendees if you wish to view the webinar again. As an added benefit to our Doble clients, our recording today, along with past recorded webinars, can be viewed on demand by logging into the Doble portal and clicking on the link for Doble webinars. A reminder that Doble clients are those companies who are members of our annual Doble service program with a valid Doble service agreement. Now it's my pleasure to introduce today's presenter. Norbert Gilbert is a senior principal engineer for Doble Engineering who has over 20 years of testing experience with the company. Norbert has published papers on transformer failure statistics, phase-shifting transformer testing, and bushing testing. He is currently the secretary for the Doble Client Transformers Committee. Prior to Doble, he spent over 15 years with Ebasco Services, providing engineering services necessary to construct nuclear and fossil fuel power plants. Norbert received his BSEE from Northeastern University in Boston, Massachusetts, and is a licensed professional engineer in the state of Massachusetts. Norbert, you have the stage.
Thank you, Monty. Thank you, everyone, for attending this webinar. And by the end of this webinar, you should be able to confidently test the overall insulation of three-winding transformers. As you might imagine, a three-winding transformer is a little more complicated than a two-winding transformer, which many on the call here on the webinar may be aware of. But going through the procedures here, you'll see that it's very easy to do, and DTA helps, that's Doble Test Assistant, helps with the procedures. So let me continue. The presentation will follow this outline. There'll be an overview of the power factor and capacitance testing. There'll be a section on apparatus and personnel safety, because that's very important to any testing regimen. The transformer dielectric circuit for the three-winding transformer will be explained. And then there will be overall test procedures given for both the M4100 and the M7100, which are the two most premier Doble testing equipment now available. There will also be a section on power factor temperature correction factors. Then we'll go into how the test results are analyzed and the recommendations. Various winding configurations will give some unusual results, which will be explained. And then a summary will be given on the whole presentation. So overall transformer insulation, power factor, and capacitance tests. Now, why do we do these tests? We're testing the overall insulation of the transformer. And what we're trying to do is assess the condition of that insulation. Now, we found that during these power factor tests that the dielectric losses and the percentage of power factor are related to the wetness or the dryness of the insulation, if if there's any contamination or deterioration of that insulation. So this test, over time you can identify if your insulation is becoming contaminated or deteriorated. So it's a very important test to perform. And results of the overall power factor test can reflect the condition of the windings, the barriers, tap changers, bushings, and oil. And I'll go into some detail further on and explain how these are identified. One significant thing that we found also is that the capacitance of these overall tests, if it indicates the physical orientation of the windings, and it can easily detect movement of the coils or the windings. You can see on the right-hand side of the screen here that there is a winding that's been an inward buckling that was identified by the overall test. Now, we want to make sure that during any testing that you are safe. So I'm going to go over a few safety concerns. Now, I show the M4100 and the M7. The M4100 is at the top, and here's our newest version of test equipment, the M7100. And the testing, the safety procedures during testing are very, very similar, so I'm kind of putting them together. We want to make sure to first isolate and ground the apparatus under test. And so you want to make sure that, of course, the connections to that apparatus are grounded before you remove them, and to work between visible grounds. That promotes a safe environment for testing. You want to make sure the instrument is grounded. You want to inspect the test leads to make sure that there's no issues with the test leads, and connect the test leads to the instrument first, and then put them up on top of the apparatus before you to run the test. Now, make sure you have good communication while testing. So in other words, like coming hot or all clear, whatever is good for your particular crew, and make sure everybody understands what the meaning of each one of the statements is. Now, you should never come in contact with the test lead while testing. And the personnel are not allowed on the apparatus while there is test voltage, right? And do not bypass or defeat any of the safety features. Now, just for example, on the lower right-hand of the screen, we show a safety switch, right? This also can be called an enabling switch, in that this switch must be depressed to the first position for the test to be able to be performed. In this particular model, if you press it too hard, it will also go off, and it will interrupt the test. And this is so that anyone that maybe will get into the test voltage will tense up and shut the test set off. This is an added test feature that is available for both the M4100 and the M7100. Once the testing is complete, remove the leads from the specimen first. So if there's any situation where you don't need a lead, you should remove it from the transformer, from the top of the transformer, put it down on the ground, and then disconnect it from the test set. The ground lead should be the last one to be removed. I didn't point this out before, but this is a picture of the ground lead, and this is the connection for the ground in the M4100. And then along this is another receptacle for the ground lead for the M7100. So now let's look at the transformer dielectric circuit. In this particular case, we want to look at the three-winding transformer. Now, of course, there are three different windings, the high voltage, the low voltage, and the tertiary. Now, from each one of those windings to ground, now that could be the grounded tank, grounded core, anything that's grounded inside of the tank is what is going to be referenced during the test. So all the insulation from the high voltage winding to ground, we will identify as CH. We used to call it CHG, but we dropped the G because it's just understood. The low to ground, of course, is called CL, and between the tertiary and ground is CT. Now also we have three other insulation systems that are between the windings. I'll point this out here. Between high and low is the CHL. Between the low and tertiary is CLT. And between the high and tertiary is CHT. So those are the 6 insulation systems that we will be testing during the testing of a 3-winding transformer. Now, it's also very good to get a very good feeling of what is inside the tank while you're doing the tests, so that you can identify if there's an issue anywhere in your testing. So the insulation between the winding conductors and the grounded tank and core are included here. Now you can have the winding insulation that is just around the windings, the low, tertiary, and high voltage bushings. Now this is the turret for the high voltage. And notice the bushings are not installed, but they would be included in the test during the overall test. Structural insulating members. Now this is something that people don't often think about, but these structural members are energized during the test. You know, it makes a difference which winding, of course, you're energized. In this case, the high voltage winding is here. Any path to ground is stressed. If they were tracking along that insulating member, it could be identified with the test. Now this is a good picture, and then it shows the de-energized tap changers right here. Now that's the DETC. Now, as the name implies, the transformer must be de-energized to move this tap changer. And the overall test tests the insulation from these devices to ground. Right? Each one of these will be energized and tested to ground during the high voltage test usually. That's where the DET is usually located, is in the high voltage winding. Now the load tap changer is shown here, and these of course are energized when the low voltage winding is energized, and they will be stressed during that time. And then of course insulating liquid, of course, or fluid surrounds this, and that will be also stressed during the ground insulation test. Now the inner winding test is a little different in that you get the insulation that's between the high and low and tertiary windings. It could be the winding insulation. Now this is the insulation right here that we're talking about. The insulation barriers, like this is the part of the barriers. The spacing blocks are these right here. The craft paper tubes are these large cylinders here, and the insulating liquid. Notice there are no bushings, no load tap changer in this, because those are not part of those tests of insulation. So it's good to be able to know what is in the test that you are doing. All right, now DTA, or Global Test Assistant, is used to make sure that we get consistent test results. And this is the form that we use. And the thing that's nice about a 3-winding transformer test procedure is it's actually 3 2-winding transformers that we do in series. The first one contains the high and the low voltage winding. The second one is the low and the tertiary, and the third one is the tertiary and high. And I'll go through this in a little more detail so you can understand. So here is the 3-winding transformer test procedure for the M4100 users. Remember, test voltage, we want to make sure that we use the proper test voltages. These are published in our books and in DTA, so but the main thing to remember is if your winding is rated greater than 12 kV, you can test at 10 kV. Any other lower voltages, you want to look it up. So, test procedure. Now, one thing we want to make sure that you do is to short the windings, because not shorting the windings can cause some unusual test results. So we short the high side, we short the low side, and short the tertiary. And then the inside DTA, we indicate where the high voltage, the red, and the blue low voltage leads are connected. And notice the high is on the high voltage winding is here, the the red is on the low, and blue is on tertiary. And this is the first two-winding transformer that we're going to test. So here is the first two-winding transformer. We're energizing the high, and we're measuring both low and ground. We get CH plus CHL. That's test number 1. Then we go to test number 2, where we measure only CH. Then we go to test number 3. We get test CHL. Now notice this is all automatically done by the test set. You just have to make the right connections. Then we rotate the leads, and this is quite easy in that whatever lead is on the high side, you will move to the low. Whatever's here, you move to the tertiary, and whatever's in the tertiary, you move to the high. So now the high voltage lead will be on the low voltage winding, the red will have the tertiary, and the blue will be on the high side. And again, it's written up in DTA, the connections. The shorting of the bushings remains the same. Now we're energizing this, the low voltage winding, so we're measuring this two-winding transformer, right? And then, of course, we go to test number 6, where we measure only the low voltage winding to ground. Then we change it to the 7th test, and notice that we now go from the low to tertiary. Okay, so we've got the second two-winding transformer completed. Now the third test setup, or the third transformer, is between the high and the tertiary windings. We've rotated the leads again. We take whatever is on this lead, on this connection, and move it here. Then we take the red lead that was here and move it up to here. We take the blue lead and move it over to here. Again, if you forget the procedure, you can look at the connections in DTA. The short-circuiting of the bushings remains the same, of course. Now in this third two-winding transformer, we now are energizing the tertiary, and the CHT and the CT are being measured. That's test number 9. Notice that CT goes to ground, and the CHT is grounded by the low voltage lead, so you measure both. One thing I want to point out here is the low voltage winding in every one of these tests is guarded away. So that low voltage winding disappears to the test. Then we automatically go to test number 10 with the software, right? And we get CT. We get the CT insulation only. Notice if you follow the circuit, you'll only measure what's going through the ground lead. Remember, the ground lead is a measurement lead. It should be connected right on the tank. Okay. Now, any other insulation is guarded away. Notice it's guarded away and is not measured. Now, the test number 11, we measure the inner winding insulation between the tertiary and high, and notice that we only measure that one circuit. Everything else is guarded. One thing I should note, be very careful when you move to the tertiary and you're energizing the tertiary, because it may have a much lower voltage rating than the high and the low voltage windings. If it's 4160, you do not want to put 10 kV on it. You want to put 2 kV only. Now, the test procedure for line 13 is what we call the check test. Of course, you've already got jumpers here, here, and here, but what we want you to do is include additional jumpers here and here. And that makes it so every bushing is going to be energized at the same time, and we'll measure all of the insulations to ground. The insulation of CH, CL, and CT will be measured. Notice you do not need any low voltage leads for this test. All the insulation all the current is going to be coming back through the ground lead. Remember to drop the low voltage lead to the ground and then disconnect them from the test set. Here is the test right here. You're measuring CH, CL, and CT in parallel, so you're measuring all those insulations. Now, for M7100 users, the procedure is a little quicker. You have less trips up and down the ladder. Now remember, while we were doing those tests, while we were applying the voltage, no one could be up on top of the transformer. M7100 users don't have to do as many trips, and let me show you that. For 10 tests, we short the windings as usual, and then for that one test, we short every one of them. That's very similar to the M4100. But what makes it a little different is we have two high voltage leads with the M7100. We have an HV1 and an HV2. And both these leads can apply voltage or as a source, or it can be grounded, or it can be guarded, or it can be measured. So it's got 4 different functions for each one of the high voltage leads. Now the M3 lead is only a measurement lead, or a ground lead, or it can be grounded, but it is cannot supply any voltage. And then of course the MG is a little different identification for the ground lead. So the test procedure is very similar, but now we notice we have an HV1 and an HV2 in the M3 lead. For test number 1, we energize the high voltage, right? The test set does all the connections necessary to get that energized. And then this is grounded, of course, and then this is grounded through the test set. Then test number 2, we only measure CH. And then test number 3, we measure only CHL. Notice that that high voltage lead 2 is actually a measurement lead now. Then we do not have to change the leads connections. So in other words, you don't have to go back up on the transformer to do tests 5, 6, and 7. And that's done this way. So you energize the H2 lead, and these 2 insulation systems are energized, and you will measure those. And then the test set continues on with its multiple tests. Number 6, it only measures the CL, right? And I notice that the CLT is not being measured. And then the last one, the CLT is measured, you energize here, and you measure the tertiary. All right, now you do have to move the leads for tests 9 through 11. And what you do is you switch these 2 leads. The HV1 stays right where it is. Only the HV2 and the M3 leads change. Now, notice that these 2 have switched. So now, we now energize the HV2, and we get these 2 insulation systems. This one, of course, is being measured, and this, of course, the ground is being measured. So we get the lumped system of CT plus CHT. Then we do the CT, and then the test set automatically goes to the CHT. Now, also for test number 13, of course, we have to go back up on top of the unit again to put the shorting jumpers on, to connect the HV. Of course, the HV1 is already here, but we have to take the HV2 down, the M3 cable down, and then disconnect it from the M7100. After we have this set up, of course, we are doing these tests here. We're energizing all of the windings at once. Be careful with the voltage again, and we'll measure CH plus CL plus CT. So these are the measured results that we just went through. 1 through 3 are for the first 2-winding transformer. 5, 6, and 7 are for the second 2-winding transformer. 9, 10, and 11 are for the test for the third one. And then the overall test where we're testing all the insulations to ground is number 13. Now we also have some calculated value. That's why we're skipping around a little bit, in that this 4, 8, and 12 are calculated values, right? And they are obtained by taking this value and subtracting this value to get this value. And CH plus CHL minus CH, of course, would be CHL. So this is a calculated CHL. And as you might expect, the measured CHL and the calculated CHL should be very, very close. And let's look at that, 3 parts in 45,000. So it's exactly the same as far as I'm concerned. And then, of course, the watts are done the same way. You subtract these two to get this value, and as I explained before, they should match up fairly closely. Now, there's also a calculation for this 0.27 here. That's 10 times the watts divided by the current to get this value. And then the capacitance is done the same way. This minus this equals that, and these two are very, very close. And the line number 8 and line number 12 are calculated in the same way. And you can notice very quickly that they match up very nicely. You know, they look at that, within 1 part in like over 124,000 parts. So they match up very closely. And then the overall test number 13 is, as we call it, is a check test. We take and add these 3 capacitances together, and in this particular case, it's that number right there, and then we compare it with the number that we measured. And notice this is very, very close. It's what, about 40 parts in 14,000. And if it's too far away, we'll flag it that something might have been done wrong in one of these 4 tests, or some of those 4 tests. Now, the power factor is corrected for temperature related to, of course, the temperature of the apparatus and the kind of preservation system that the transformer has. I'm going to explain how that works. Here is the correction factor for an example test, and it's 0.92. Now, where does that number come from? Well, previous to the DTA software, we used to publish this chart or this table in paper form, and I've just put it in this presentation so you can see where it came from historically and how it's used in DTA. Now, as I mentioned, the weather conditions for the particular test that I just showed you, that the apparatus temperature was, this is the top oil temperature, was 35 degrees C. So that on the chart is right there. There's the C, 35 degrees. Now, it doesn't make a difference what the air temperature is. It's the apparatus temperature we want, because the air temperature doesn't affect the overall test that much. It could actually be below freezing, and you still get representative tests. And then, of course, the tank type that was chosen by the person doing the test is a nitrogen blanketed, and it's an oil coolant. So that's the oil filled. It's a power transformer, by the way, and it's gas blanketed, and that's how you get that value of 0.92. It's right out of the chart. Okay, now how do we analyze the results? Here we've got some nice numbers and everything, and we want to say, what's the value of these? Well, we do what we call tabulations of many, many test results. Now, this is just, a small sampling. We've got thousands and thousands or more in our DTA web. But this is like 240 of the tests for CH in this particular sampling had power factors in the 0.3 range, right? And they had 180 around 0.4. And this is how we identify the locations where we're going to put the limits. And notice in this particular case, all these power factors are below 0.5, and we've given them a G rating. Now, what does that G rating mean? Well, it's good condition, acceptable for service until next scheduled test. So in other words, you can now do a routine test in 5 years, 6 years, whatever your recommendation is. Deteriorated, not as good as before, and retest in a year or less to monitor the installation condition. You know, what is the trend? Is it getting higher, or is it just staying where tested previously? Investigate. Test results show a problem. You should investigate. Bad. Not suitable for service. Keep away from, out of service until the condition is clarified, or you may have to replace the specimen. Nameplate data is incomplete and DT is unable to determine. That's when you get a Q rating. Now, to get a little bit more detail, a distribution transformer is 0 to 500 kVA, very small unit. And as you might expect, the power factor limits are fairly high on those. But when you get into power transformers, greater than 500 kVA and less than 230 kV, we have a more strict limit on the power factor. Remember, a lower power factor is better, right? So anything below 0.5 in that in those ratings would be given a good rating. Now, when we get a greater than 230 kV, we even become more strict, where we don't want you to go over 0.4 to get a good rating. Anything between 0.4 and 0.6 is deteriorated. Anything greater than 0.6 will get an investigate. Now, I had mentioned that the change in capacitance is very, very important. Between 0 and 5%, you'll get a G rating you won't notice. Between 5 and 10%, we will get a D rating. Even if all the power factors are good on a particular insulation, if it's between 5 and 10, you will get a D. And if it's greater than 10% change, you'll get an I rating. So let's look at some results with various winding configurations. These are quite interesting. In this particular case, we show that the CHT will have a low current. Now, why is this? Now, during the CHT test, you're energized in the tertiary winding and trying to measure to the high voltage winding. Well, notice that the low voltage winding is in the way. And in that particular test, the low voltage winding is grounded. So in UST, the low voltage winding being grounded, the current trying to get to the high voltage winding is guarded away. It is not measured. So it almost makes the high voltage winding disappear. You are only getting the skirting effects around the low voltage winding. Of course, it'll happen on the bottom also. So you're getting very, very low values. Notice that in this case, this is a case right here where that's the situation. And notice it's less than 1 milliamp. That's the way we identify that there may be a shielding problem or a shielding situation. I don't want to indicate that this is a problem. It's just the situation. So that's why this is very low. Notice comparison, it's 41 and 21 milliamps for the other insulation system. Now this one was given a bad rating because it didn't match up nicely and everything, so this was given a bad rating, but we informed the client that this was okay because of the low currents. Now this is another situation that we found where the CLT will have a low current. And the reason for this is because this is a stacked winding. Often these two windings will have the same rating, 4160 volt. It's a auxiliary transformer at a power station. And the reason this has got a low current is because the capacitance is very low here. The area between these two windings is very small compared to between high and tertiary and high and low. Here's an example of that. Again, under 1 milliamp, and notice that it's very consistent though, so there's really no problem, but it's a lot lower than the other currents. Notice also that these currents here and here are very similar because those areas are very, very similar. So this, again, is not indicating a problem, it's indicating a particular construction of the transformer. The last case I wanted to show is the winding configuration actually caused a negative power factor. Notice how low these currents are. This is like 1/100th of what the limit we usually say is around 1 milliamp is where we'd say that's very. So the engineer that was asked about about this case went to the manufacturer and said, how is this transformer built? Why are we getting these results? And this is what they had identified to him, is that the low voltage winding is on one leg of this single phase transformer, while the tertiary winding is on the other leg, and the high voltage winding is actually split between the two legs. When the test in question, number 7, the CLT test, we are energizing the low voltage winding and trying to get to the tertiary. Notice again that the high voltage winding in this case is guarding the two. So that's one reason you're getting a low current. Well, the other reason is, look at the distance. The current will go down because of the increased distance between two windings. So there's two reasons why this current is very, very low. The shielding effect and also the distance. In summary, the power factor test assesses the condition of the insulation quality. Those list of 4 things in there can tell you, can cause higher power factors and indicate a problem. Now, the capacitance tests are a measure of the structural integrity of the transformer. When you compare to a previous test and the capacitance has changed significantly, we usually say significant is over 5 or definitely over 10% shows a structural integrity issue, and it could indicate that winding has moved. Now, the test procedure breaks up the apparatus into several insulation systems. What we mean by that is that we, let's say for tests 1, 2, and 3, we have CH plus CHL, and then we break it up so that we measure CH separately and then CHL separately. So each one of the smaller insulations are tested. And a key point to remember is testing a 3-winding transformer is the equivalent of testing 3 2-winding transformers. Remember, the procedure is all in DTA, so it's difficult to do it incorrectly. You want to trend results over time. So in other words, pay attention to changes from one testing year to another. Also, certain winding configuration can result in low measured currents and high, low, or even negative power factors, but don't indicate an issue. And some key points to remember is that for testing, service providers definitely save the electronic results and print a hard copy and provide that electronic copy and hard copy to the owner of the apparatus. For apparatus owners using the test service providers, refer to the printout to assess the condition of the insulation and make sure to request the electronic copy so that you have it available. And that electronic file can be used using DTA, and it can also be used for repeat tests, so that for the next service provider. And also, of course, if you want to test it yourself, of course, you can use that DTA for the owner to test it. And that completes my presentation. Thank you.
All right. Thanks very much, Norbert, for today's informative webinar. We do have a few questions here, so I'll get started. First question. For tests 5, 6, and 7, it says you don't move the 2 high voltage leads, but do you have to change the connection to the test set?
The answer is no. You do not have to change the connections at the test set. The test set has the ability to make the necessary connections in the box. So what you can do is you can actually run tests 1 through 3, get those tests completed, then you can choose tests 5, 6, and 7 and run those tests without any lead changes at all.
Okay, very good. Thank you. So next one says, says you have all the capacitors in the measuring circuit on your diagrams. How how do you get the capacitor value between the two windings separate from the phase to ground value in the device?
I didn't understand the question, Monty. Could you say?
So it says, in looking at the diagrams, you have all the capacitors showing in the measuring circuit. How do you get the capacitor value between the two windings separate from the phase to ground value in the device test?
Yeah, I think I understand. I'm just going to go to one example. Yeah, let's just look at this example here. In the three-winding transformer, you of course have all the insulation is there. It's just how we apply the voltage and how we measure will determine which capacitor we're going to be measuring. So let me just point this out. In this particular case, we're going to energize the HV1 lead, and the high voltage winding will be energized. In this particular case, test number 1, both of these windings, insulations, right, will be tested. Let me show you how that works. The CHL, you follow the current down through CHL, and that goes through the measuring network and will be measured. The current going through CH will go down through and go through the ground lead and be measured. So in other words, it's how the test set connects the leads to the measuring network. I'm going to go through 2 more slides. Notice again, we're still energizing HV1 for test number 2. We follow down through this circuit, and notice we measure. Notice that anything going this way is guarded, is not measured. See how it did not go through the measuring network? And then I'm going to show this one also. Notice it does not go through the measuring network. And lastly, when I energize this and go down through this capacitor, notice I measure that one. Any current going to ground is not measured. See how the current through that circuit does not go through the measuring network. And lastly, if you follow down through this insulation, notice that is also guarded. Hopefully that answers your question.
Very good. Thank you, Norbert. Next question. Do 3-winding transformers have a neutral link? If so, do you need to disconnect it before testing?
A neutral link. In other words, a neutral ground? I think that might be... Okay, let me just explain what I think he means. If there is a ground for any one of the bushings, that must be removed. Now, one other situation that he might be considering is when you have 2 Y-connected windings, sometimes there is a link between the 2 at the neutral point, and that would have to be disconnected to be able to test those 2 windings separately. If you cannot get to the link, then you are forced to test that as 1 winding. I think that's what he probably was questioning.
Okay, thank you. Next question, what is the purpose of the tertiary winding?
Okay. Tertiary winding, now, Doble is not an operations type company. We're more of a testing company, of course. But the tertiary, from my understanding, is usually to provide either an additional voltage, like in a power plant. You can often have 2 voltages sent into the power plant to run auxiliary equipment, 2 separate circuits, right? So that's why you'd have a low and a tertiary winding. In another situation, you may use that tertiary winding for substation power, where the high and the low are the main circuits, but the tertiary is for some substation power, for auxiliary power. Now, the tertiary in a three-winding transformer shouldn't be confused with a tertiary for a auto transformer. A tertiary on an auto transformer is used to make sure that like zero sequence currents and stuff are taken care of. But in a three-winding transformer, it's a little different situation. That is not there for stabilizing. It's more for operational reasons.
Very good, thank you. Next question is power factor an applicable test for current transformers?
Yes. Of course, that wasn't explained in this webinar, but yes, we do recommend CT testing as power factor testing for CTs. The test for a CT is very, very simple. You short the H1 and H2, perform a test to ground at the highest voltage that is applicable for that CT, and then we'd like to have it tested at a lower voltage also. Let's say that you can run the first test at 10 kV, then you'd run a 2 kV test, and then you look to see if there's what we call a tip-up. Usually those two tests should get about the same power factor. A tip-up might indicate a problem.
Thank you.
Good questions.
What is the significance of negative power factor?
Okay. In that particular example I gave, the negative is likely due to it being a very low current, first of all, and also we find that during a UST test, which this is definitely a UST test, right? It's an ungrounded specimen. Let me go to that slide. Yeah, it's more than likely this one here that gave the low current. Notice that you're energizing this, and you're energizing the yellow one. I'm sorry, and measuring this one. So it's what we call an ungrounded specimen. Well, if you have in a low current situation like you have here, any path to ground has a tendency to make the measurement that you're measuring go negative. It's just it's the physical situation that you have with the transformer. It will make the test go negative or make it go lower than it actually is. We find this quite common on ungrounded specimen tests where you have a high resistance path to ground. There's been probably 3 or 4 papers written on this. I would suggest go to the portal and read those because they're quite interesting in how that phenomenon of a negative power factor is quite common in testing.
Very good. Next question, Norbert. How would the bushing influence the UST current when testing between the high side and low side windings?
Very good question. Very good question. I pointed out, and it maybe was not very clear when you first saw it, is notice that in the insulation, I went the wrong way. In the insulation circuit, there are no bushings listed during the interwinding tests, and that's because they are not included. Yeah, it's going to take too long to get there. Is that when I'm energizing the high voltage winding and I'm going to the low voltage winding, of course, I have it's done as a UST test, right? Well, anything that is grounded during a UST test is not measured. So the bushings are not tested during the ungrounded specimen test. Yeah, here it is right here. Notice that in this list, for any of the interwinding insulations, there are no bushings tested. And that's because when you go from the bushing center conductor to ground, that is being guarded away. So the bushing, in effect, disappears during the interwinding test. Okay, next.
Very good, Norbert. Next question. Is there any residual energy that needs to be dissipated between tests?
Good question, good question. Yeah, we've made sure that the design of the test set is such that it fully discharges after a test has been completed. Now with the M7100, we also have a additional warning that if for some reason the test gets interrupted and wasn't completed, that we put a message up there to say that there may be residual energy in the circuit. In that case, I would recommend that you definitely ground out that circuit prior to touching it, just in case. But if it goes through the process properly and finishes the test, there should be no residual. Now, one thing I want to point out, another safety feature is that, remember, the test set only provides the test voltages, but there are other sources of voltages in a substation. There could be static charges and induced charges. So if there is any conductor in the substation, including the transformer, that is ungrounded, it must be suspected to have charge on it. So be very careful operating, making connections to a transformer. Even though it isn't connected to the outside world, it may still have picked up some charge. So do it safely with proper techniques.
Thank you. Should we still be performing DC insulation resistance tests on these transformers in addition to power factor testing? What would your test voltage be for a 345 kV transformer?
Now you're talking about, well, of course you can't ask the question. Okay, for insulation resistance testing, the recommendations that Doble would make would be that they can be performed. They may find a problem that the AC test might not. Now I'm identifying that as because this is normally a DC test, or can be a DC test, right? And it may energize the insulation differently. But if that winding insulation test is an AC test, more than likely it's going to show the same things. One thing that I want to be very clear is that insulation resistant tests done with a DC test, even the manufacturer of that equipment usually says that a PI for that type of insulation is not going to show any significant issue. Even if there's something wrong with the insulation, the PI test will probably not identify it. But that's something that you need to look in the instruction manual for the insulation resistant test very carefully to see their recommendations. Remember, this I'm a Doble employee. I make recommendations on Doble tests, so be careful with the winding resistance. Now that I've said that, of course, the M7100 kind of blurs that line a little bit, because now we are doing insulation resistance tests with the M7100. So we're going to be learning more how we can analyze those results better. Next.
Okay. What happens if we have a buried tertiary?
Okay. A buried tertiary means that no bushings are brought out of the transformer for connection. In that case, it would be tested as a two-winding transformer. You have to have the ability to connect to the winding for it to be a viable test point, right? So a 3-winding transformer with only bushings from the low and the high voltage could only be tested as a 2-winding transformer.
Okay, thank you. I'm not sure if this is applicable, but I'll do it anyways. How do you do an excitation current test for a transformer that is a too close of a ratio, meaning the high side voltage and low side voltages are almost equal?
You did say exciting current?
Yes. Excitation current.
Yeah. The excitation current can be done on any transformer, no matter what the winding ratio is. That's not a significant issue with running an exciting current test. The important thing is that both low and tertiary windings have to be isolated, of course, from ground and also not short-circuited. And when you run the test, the excitation current test, it'll be from the high side. And the ratio between those windings or the voltage ratings of those windings should not make a difference on running those tests.
Okay, thank you. So if there is any leakage in the transformer tank at the top, can we perform power factor testing, or it's not recommended until the problem is fixed?
I know you can't answer the question, but my question would be, when you say leakage at the top, you mean a nitrogen blanket leak? I think is what he's probably saying, so I'm going to answer the question that way. A leak in the transformer, of course, that allows oil or nitrogen out during its lifetime will also allow moisture to go into the transformer. Now, the power factor test is a great way to identify if indeed that may have happened, right? Because moisture will make the power factor go higher. So so in other words, a leak in the transformer is not a reason not to do the test. Test can definitely be performed. Now, but if you really feel that the transformer is wet, let's say you've already done some oil quality tests, you know it's wet, you might want to dry it out even before you do the test. But also, you could do the test ahead of time, perform your dry out procedure, right? Fix your leak, and then test again to see how well your dry out procedure was. Remember, make sure that you put the oil back in prior to doing the test again, unless you are very careful to purge the unit of oxygen.
Okay, and last question. During a test, we found that the conductor from the core/clamp, from the inside of the winding structure to the core clamp bushing compartment on the top of the transformer tank was defective, meaning the insulation for the conductor was defective. While performing power factor, would this issue be detected?
The answer is yes. Well, okay. If there's still a electrical connection between that ground bushing, the core ground bushing, and the core, there's still electrical connection, it will still test probably about the same as it would have with a good connection. Now, if that connection is not there, it's definitely disconnected, you will see a very large difference in the capacitance. We have seen this previously, is that people have forgotten to reconnect the core ground external to the transformer and perform the test. and you'll get quite different capacitances for all the tests. Well, the UST test will be about the same, but the GST test or the ground test will be quite different due to that change in the core ground configuration. That's why I'm a little unsure of the question. I think he's saying that if it's just a bad connection with that show. I haven't had experience with that, but I'm kind of wondering if you might get a little higher losses during some of the ground tests. I haven't got experience with that, if that would definitely be the case. But I'm thinking that poor core ground connection having a high resistance might show up in higher losses and higher power factor in some of your ground tests. And then just to clarify one more thing, is if your core ground is not made, you will definitely see a large capacitance change. Hopefully that answers your question.
Okay, thank you, Norbert. We have others, but we're going to have to move on, and we'll address those questions separately to the recipient who asked them. So thanks very much. Before we wrap up, I'd like to mention that Doble hosts technical webinars each month on apparatus field testing and maintenance. Our next webinar will be Wednesday, August 7th at 1 o'clock p.m. U.S. Eastern Time, and the subject will be Field Diagnostics for Surge Arresters, presented by Bob Sarney, Principal Client Service Engineer at Doble Engineering. You can sign up using the link shown on our website. Doble will be hosting a client field seminar in Orlando, Florida during August 27th to 28th. This is a valuable opportunity for supplemental training on apparatus testing with technical presentations similar to our webinars, along with many case studies. Registration, venue, and information on the seminar is available at the Doble Events link on our website. The seminar is free of charge for Doble clients. A fee of $395 is charged if you are not a Doble client. Again, the link to view the recording of today's webinar will be sent to all registered attendees in a few days. The link will expire by July 29th. If you are a Doble client, you are entitled to view our recording today, along with past webinars at any time on demand by logging into the Doble portal and clicking on the link for Doble webinars. If you would like to get continuing education units or earn one professional development hour, please answer the question related to our webinar today in the feedback form, which will be sent to you at the end of the webinar. A certificate for credit will be sent within 4 weeks to those who complete the question. In closing, Norbert and I would like to thank all of you for attending today's webinar on testing three-winding transformers. If you have any further questions on today's topic, please contact Norbert directly at his email address, which is ngilbert@doble.com, or you may contact your Doble Client Service Engineer, or use the Contact Us link on the homepage of our website. Again, our presenter today was Norbert Gilbert at Doble Engineering. My name is Monty Shigi, and I hope the webinar provided you with useful and valuable information. Please look for future monthly webinars on the Doble website. Thank you for joining us, and have a great rest of the day.